NASA's plan to return to the Moon is a logistical feat involving 4 astronauts and 3 separate spacecraft. To succeed, these vehicles must perform a synchronized dance through deep space. This modern choreography is a stark departure from the Apollo missions of the 60s. Back then, we reached the lunar surface with a single vehicle and a direct shot. Now, the process looks entirely different. The reason for this complexity is a mathematical barrier called the rocket equation. It describes the exponential relationship between the mass of a payload and the massive volume of fuel required to lift it out of Earth's gravity well. For the first 50 years of spaceflight, this math dictated a specific architectural model, the expendable rocket. To reach orbit, vehicles had to shed their heavy engines and empty tanks, leaving them to burn up or sink into the ocean. To understand why Artemis 3 requires such a complex mission profile today, we have to look back at how early military pressures forced us to solve this gravity problem with brute force. The first successful attempts to beat the rocket equation relied on liquid propulsion, demonstrated by Robert H. Goddard in the early 20th century. During World War II, these fragile experiments were rapidly scaled up and weaponized into the first ballistic missiles, like the German V-2. The Soviet Union later modified this exact ICBM architecture to achieve the massive thrust necessary for orbital velocity. The result was Sputnik 1, the first artificial satellite, which sent a geopolitical shockwave through the West. This military architecture was quickly adapted to put a human into orbit for the first time, carrying Yuri Gagarin around the planet. The American response used the same multi-stage logic, but scaled it to a gigantic size. The Saturn V remains one of the largest machines ever built. This brute force engineering approach worked. It put humans on the Moon and returned them safely to Earth. While Apollo achieved its goal, throwing away millions of dollars of hardware on every flight was a financial dead end. Without a way to reuse the rockets, deep space exploration effectively stopped for decades. After Apollo, NASA changed its approach. The new goal was to build a vehicle that could return to Earth and be flown again, making access to space routine and affordable. The Space Shuttle was the result, the world's first partially reusable spacecraft. It proved capable of deploying critical scientific infrastructure, including the Hubble Space Telescope. Its primary legacy was serving as a heavy-lift construction vehicle, allowing humans to assemble and inhabit the International Space Station. However, the shuttle's extreme refurbishment costs failed to solve the economic problem. It showed we could build in orbit, but it wasn't yet the cheap access to space NASA had promised. A new model eventually emerged from the commercial sector. The idea was that rockets should operate less like expendable missiles and more like commercial airplanes. Reusability requires a rocket to do the impossible, survive atmospheric re-entry, and use its own engines to perform a controlled, vertical touchdown. Mastering this technology allowed companies like SpaceX to turn the rocket into a reusable workhorse, bringing launch costs down to a fraction of expendable systems. This created a split in modern philosophies. NASA refines expendable systems for the Space Launch System, prioritizing maximum reliability for journeys through deep space. The SLS carries the Orion capsule, which is designed specifically to protect astronauts from the extreme radiation and re-entry speeds of a lunar mission. Contrast that with the fully reusable, stainless steel architecture being developed for the landing itself. The modern era is defined by this divergence: government reliability for the commute, and commercial infrastructure for the destination. On the Artemis 3 mission, these two competing designs must work together. First, the NASA-built SLS launches astronauts toward the Moon inside the Orion capsule. Separately, commercial Starship launches as the landing system. It requires refueling in Earth orbit by several tankers, before traveling to lunar orbit, docking with Orion, and carrying the crew to the surface. This complex logistical dance is currently the only way to merge the deep space safety of legacy rockets with the massive payload capacity of modern reusable systems. This approach is far more complex than the Apollo era, but it serves a different purpose. Brute force expendability worked for a geopolitical race, but it couldn't sustain long-term activity in space. Moving toward reusable components and commercial partnerships changes the economics of spaceflight. It provides the heavy lifting required to build habitation and industry off-world. We are seeing a transition in how we use space. We are no longer just visiting as temporary guests, but building the architecture required to turn space into a permanent frontier.